So today we're going to do section 4.2, identifying extrema, something called the first derivative test. So the game, we're still playing the game of finding extrema. So recall, somebody gave you a function, right? Somebody gives you a function on a closed and bounded interval, say, right? And it's continuous, and maybe it's also, in fact, it's differentiable. We actually know that that this function has extrema, right? The extreme value theorem, so extreme value theorem says that f has, f attains a max and a min, right? F attains a max and a min. Okay. So, and then we have some way of finding those points. How did we find the points? Where? How did we find the max and the min? Yes, Sarah.
Find when the derivative equals 0.
Find when the derivative equals 0. So we consider points where the derivative equals 0, and maybe I shouldn't say it's differentiable. So like sometimes it's differentiable and sometimes it's not differentiable. What other points do we consider? Right, wait.
Undefined.
The derivative is undefined. Right. Derivative undefined. Right. Or places where f was not defined on an open interval. F not defined on an open interval. Right. Around that point. Okay. So if it's an interval, then this is basically endpoints. Endpoints. Right. Endpoints. Because you have your function a b, and at b, your function isn't defined in the full open interval. It's only defined on sort of this half of an open interval. Okay, so that was the game, right? To find where the extrema are, you say, well, they have to be at these points. They have to occur at this sort of point, and then you just evaluate the function at each point, each such point, and see which is biggest. See which is biggest and which is smallest. Right? And so that was basically our method. Right? See which is biggest or smallest.
Does that say around that point?
Yeah, around that point. Let me remind that these guys are called critical points. Okay. Where the derivative is 0 or undefined, those things are called critical points. So you look, you find the critical points, and then you check the critical point, the values at the critical points at the end and at the endpoints, and you see, which point has the biggest value and which point has the smallest value. The biggest one is going to be the max. The smallest one is going to be the min. Okay, and so this is the way of finding. This is sort of how to find the global max and global min for f continuous on a closed and bounded interval AB. But it doesn't give you any information about if a point, if a point is a local max, this method won't pick that up. Right? This tells you nothing about if a point is a local max or not. Right? It'll just say, oh, the greatest value occurred here and the smallest value occurred here. But it won't. It'll for this. It'll say, I don't know. This method will say it's not. It'll just say it's not a global maximum. Yes, Sarah.
But wouldn't you be able, like, you've been able to tell like where the derivative is 0? So
Yeah.
couldn't you say that like this is a point where the derivative is 0, and then say that it was like some kind of critical point?
Not necessarily. So all you'd be able to say is that the derivative is 0 there, but that doesn't necessarily imply that it's going to be a max or a min. For example, you can have something like this,
Oh, right. Okay.
right? The derivative is 0 here, but it's not a max or a min, right? So all so far we can't say anything about such points. We can tell where the global max is and where the global min is, but that's about it. Okay, so this is our method at this point is pretty crude, but we can use the observation that we made last time. So recall last time we said if f prime is positive on an open interval I, then f is what? If f prime is positive, then what do you know about it?
Increasing.
F is increasing, right? By the mean value then. And the mean value. Right. Right? Because remember, it'll tell us that the slope, if you take, so here's your open interval, if you take any 2 points in there, then the slope has to be bigger than 0, right? The slope has to be bigger than 0, so that means that the slope of this line between those 2 points has to be bigger than 0, and so the point on the left is lower than the point on the right. Right? We did this last time. Okay, and this is going to be how we figure out where how we get information about local maxes and mins. So let me show you an example. Okay, so consider the function x cubed plus 3x squared minus 45x plus 2 on all of R. Okay, I'm going to ask you to think for, spend 2 minutes answering the following questions. 1, where are critical points? 2, where is it increasing? Where is it decreasing? Okay, so take 1 minute, maybe 1.5 minutes, and see if you can say anything about it. Okay, see if you can answer these questions. Oh, I should also say, there's, if f prime is less than 0, then it's decreasing. Right. So there's an analogous statement. Right? If f prime is positive, you have an increasing function. If f prime is negative, you have a decreasing function. turn to somebody next to you and say, here's what things are looking like?
Sorry. I messed up my factoring because I thought for some reason No, it doesn't. I don't know why. I just looked at 3 and I was like, 9. So then you do the first
Okay, who would like to talk about it? Who would like to talk about it? Maybe somebody who doesn't normally talk. Anybody? Colton is volunteering. Nico?
So I took the derivative.
Yeah. What do you get?
So I got x squared plus 2x minus 15. Or sorry, 3x squared plus 6x minus 45. Equals 0.
Okay, so you set that equal to
So
0?
I set it equal to 0.
Okay.
I'm going to solve for 0 to get the critical points.
Okay.
So I divided everything by 3.
Okay, so you get x squared plus 2x minus 15 equals 0.
And then I factored that x plus 5 times x minus 3. So the critical points were -5 and 3.
Okay.
So then I made like a line there. So at -5 and 3, so I tested
Right.
points like, so I picked -6, 0, and 4.
Okay. And you
So I got a positive, like from negative infinity to -5, then negative, then positive.
Okay. Yeah, so basically you remember that you were forced to play this game in pre-calculus a lot, right? Where is your polynomial positive? Where is your polynomial negative? Right? And the way you did it was by finding the roots of the polynomial and then testing a point in between, right? Testing, and you say, well, if these are the zeros, then the sign of my polynomial is not going to change, and so it's going to be, I just need to check one point in here, I get a negative number, so it's negative all here, it's all positive here, it's all positive here, right? Or you could use your knowledge of the parabola, right? This is clearly a parabola, and it's an upwards parabola, so you know that it's going to be negative here, and positive here, either way. Okay, so what does that tell you, right? That tells you that right, you get a few bits of information. One is that, what do you get? The information you get is that that there are extrema possible at -5 and 3, that the function is increasing on negative infinity from a -5, decreasing on -5, 3, and increasing on 3 infinity. Right? So it's increasing, the function, the original function, right? So f is increasing, right? The original function is increasing on the beginning, then it decreases, then it increases again. Yeah, Sarah?
What do you mean by increasing? Because it seems like the function is going like down on.
So everybody, can somebody say what the confusion is here? When
Since that's the derivative.
this is the derivative.
Oh, got it. Okay.
The derivative is going down and then back up again, but the original function is increasing here and then decreasing here and then increasing here.
Got it.
Okay, right. So the derivative tells you about the behavior of the original function. Okay. So what does this tell you? This actually gives you. This tells you everything. This tells you about -5. It says that before -5 we're increasing, and then after -5 we're decreasing. So what does that tell you about -5? -5 is local max, right? Local max. What about 3? Before 3 we're decreasing. After 3 we're increasing. So local min, right? So we can see, we can tell that -5 is a local max and 3 is a local min. Okay. So, right, your picture, you know, don't know exactly how it looks. At least you know it's increasing and then decreasing. Oops, decreasing and then increasing again. Right? And from your knowledge of you see that this is a cubic guy, and so it has no global max. It has no global min. Right? As you head off towards infinity, this just gets bigger and bigger. As you head toward negative infinity, it gets smaller and smaller. So no global max, no global min. Knowledge of cubics tells you there's no global max or min. Okay. Everybody understand the example? Everybody understand the example? Okay. So that's basically the first derivative test right there. That example, simple as it was, is everything about the first derivative test. So the first derivative test is just sort of a codification of what we just did. So here's the first derivative test. If f is differentiable on an open interval, and f prime of c is 0, if f prime is less than 0 before, and f prime is bigger than 0 after, then it's a local min. Right? If f prime is bigger than 0 before, and smaller than 0 after, then it's going to be local max. And if f prime doesn't change sign, then it's neither min nor max. So that's the first derivative test, right? Almost nothing to it, right? Just what it uses is your knowledge that you get from the mean value theorem that says if f prime is positive, you're increasing, if f prime is negative, you're decreasing. So, right, decreasing and then increasing means you're min, increasing and then decreasing means you're max. It's almost common sense. But what justifies that common sense is the mean value theorem. Any questions? We'll do a few examples, a few more examples. Okay, so here's one. F of x is 3x cubed plus x squared plus 4. Let's just do this one together, right? What do I need to do with it? Somebody who doesn't normally speak, maybe tell me. Do it.
You take the derivative.
Mm-hmm. Take the derivative, you get 9x squared plus 2x.
And then you factor it.
You factor it, okay, so.
X. And you take out the x. Right?
Yeah, you can take out the x and you get 9
X
plus,
plus
I'm sorry, 9x plus 2. Uh-huh.
And then one of the points is negative 2. Or,
You basically set both of these things equal to 0.
Oh.
So this equals to 0 whenever either this is 0 or this is equal to 0. Right? So you use the zero product property. Right? So now this one says that, this latter one says that x is negative 2/9. Okay. So that tells you that your derivative, right? You're looking at your derivative at 0 and at negative 2/9. Your derivative has roots. Okay. And what do you do from there, Nora? You remember this is the pre-calculus game. You say, well, I need to figure out where f prime is positive, negative, where f prime is positive and where f prime is negative. So you can test a point. So you say, okay, I take my f prime and I plug in 10, let's say, and I get something positive. Right? Because I get a positive number times a positive number, right? 10 times 92. Right? That's certainly positive. So that tells me that on this whole interval here, I'm positive. And then you test the other points. So you take some huge negative number, you get a negative times a huge negative, right? So this is positive also, right? And then you take like -1, say, and you get -1 times. Wait a second. No, not -1. -1 isn't in there. Right, you take -1/9, say. -1/9, right? You say you get -1/9 times 1, right? And so you get a negative. Right. Or, like I said, you just use your knowledge of parabolae, right? You say, well, look, this is an upwards parabola, and so I know that it's going to be positive and then negative and then positive. Yeah, no.
and so when you're testing the points,
Yeah.
you insert that point into the derivative.
That's
not
right.
the original.
That's right. That's right. Because you're trying to figure out where this guy, where the derivative is positive, negative, and positive. You already found out where it's 0, and then by your knowledge of polynomials, you know that to figure out the sign, you just need to test it in between. Okay. Because it's not going to jump over and change sign without creating another 0. Okay. Okay. So again, we have basically the same thing, right? What's this? Is this a max or a min? Max, right? This is a max, and this is a min, right? Because you go up and you go down, you go down, you go up. Okay. Okay, last one. Last example. F of x is x squared e to the minus x. So, slightly trickier one. Let's see if you can do it using your knowledge from before. Okay, so take 1 minute and see what you can get out of it. Amanda.
Oh, is it e to the minus x?
E to the minus x.
Okay. Thank you.
In some sense, this problem is no harder than the previous. You just have to use a little bit more of your knowledge. 1 or 2 bits of knowledge more. Okay, turn to somebody nearby and say, here's how I differentiated, and here's what I'm thinking.
Oh, you're right. But even though I'm out here, yeah, just wait, no, I did too. No, sorry. Really bad.
Okay, so what happens when you differentiate it? Marcella, do you want to tell me? Yeah,
So I got 3x,
Say again?
2x times e to the negative x plus x squared minus e to the negative x. Equals 0.
Don't set it equal to 0. Yeah, right now we're just taking the derivative. Anyone, something missing? Something missing? When you differentiate, right, when you differentiate this, what do you get?
E to the negative x.
At least.
Negative x times e to the negative x.
Mm,
Oh, wait.
Chain rules.
Negative 1 times e to the negative x, right? Because you differentiate, right? So, right, this e to the negative x is the, and you've got the exponential function of negative x, and you're differentiating it, right? By the chain rule, you take the derivative of this guy, evaluate it to this guy, times the derivative of this guy, right? So you need a negative 1 in there. Right? The derivative of the outside guy, evaluated at the inside guy, times the derivative of the inside guy. Okay, so this should be a minus rather than a plus. Okay, and then you set it equal to 0, 2x e to the minus x minus x squared e to the minus x equals 0. And what happens? Did anyone get that? Anyone see how to do that? Julia.
I factored out x times e to the negative x.
Okay, x e to the negative x, you get 2 minus x. Great.
That x equals 0 and x equals 2.
X equals 0 and x equals 2, right? Because again, you use the zero product property and you say this is going to be equal to 0 if and only if either this is 0 or this is 0 or this is 0, right? So you get x is equal to 0, x is equal to 2, and what about this? E to the negative x equals 0. Do you get any solution from that? No, right? E to the x is never 0, right? The exponential function, right, is e to the x, right? E to the minus x is the reflection of that, right? So e to the minus x, it never is 0, right? E to any power is never 0, right? So this doesn't contribute any solution. That's impossible. Okay. Okay. Great. Okay. So we get that the derivative is 0 at 0 and at 2, right? And then what? Elise, go ahead.
And then you can put in negative 1, and then 1 and 3.
Okay, so you just tested points, and what did you get?
I got negative, 4, 0, positive, and then negative.
Negative, positive, negative, right? So you test, right? Or again, you can use your sort of knowledge of a parabola, right? This is e to the negative x times negative x squared plus 2x, right? It's a downward facing parabola multiplied by some positive number, scaled by some positive, scaled by some changing positive number, right? So, but it's a downward parabola just multiplied by different positive numbers. So you know it's going to be negative, positive, negative. Okay, so what do you know? You know that this guy is the what? The min, right? Local min, local max. Okay, and that's it. Any questions? Okay, easy, right? After all that mean value stuff, this is peanuts. Okay. Okay. So there's always a collection of problems that could be described as just like obfuscation. Obfuscation, right, means that you're taking something simple and then making it unnecessarily complicated. You're piling a bunch of junk on top of something simple. Okay, and so that's the kind of problem that you're going to see right now. Okay. In other words, word problems. Okay, word problems, right? So you've taken a mathematical idea and you've buried it under a bunch of words. The game is a lot of the game is just figuring out what the mathematical problem is under all those words. Okay, so here's one problem. What number in the non-negative numbers exceeds its cube by the greatest root, the greatest amount, right? Here's one question. What number exceeds its cube by the greatest amount? Okay. So you take this thing and you translate it into mathematics, right? So what are we trying to look at? The difference between the number and its cube, right? So what function do I need to consider? There's an x cubed in here, but I want to look at the difference, like how far I am bigger than my own cube, right? So minus me minus my cube, right? That's what I'm trying to maximize. Okay. So the function is f of x is this, and it's on 0 infinity. Okay? And the question really is find the max. Find the global max of this thing. Okay? Right? So this word exceed is your cue that you need to look at, the difference between them, the difference between yourself and your cube. Okay. Okay. So so what do? Somebody just tell me. Take the derivative, right? F prime is going to be 1 minus 3x squared, right? So I set that equal to 0, right? 1 minus 3x squared being equal to 0 means that 1/3 is x squared. Right? And so the zeros occur at plus or minus the square root of 1/3. Right? Okay. So I know that this is 0, 1/√3, negative 1/√3. Right? My function looks like this. My derivative looks like this. Right? And let's play the polynomial trick, right? Let's play the parabola trick, right? What can you say about this?
It's not just like.
Right? It's a downwards parabola, right? And so it's going to be positive here, negative here, negative here. Right? So, yeah. No.
How did you get 0 as one of?
It's not, I'm sorry. I just put a 0 there because I wanted to give you some
Oh.
indication of the number line. Sorry. So let me put the roots down as these dots. Okay, the roots are the dots. The 0 is just there for your reference. Okay. Okay, so what's the answer? What number exceeds its cube by the greatest amount?
-1 over
Positive.
Sorry? In 0 infinity? This guy, right? Because you see that the function is increasing and then decreasing, right? So this guy, this thing attains a max here. Okay?
Isn't that only local max though?
It's a local max. It's a local max, but what you see about the function is that it increases. It starts at some value here, 0 actually, right? So here's my assumption. I see that the value of my function at 0 is 0, right? At this point, it reaches some value, and then after that, it's always decreasing, right? So in fact, it's not just a local max, it's the global max. Okay. So what you're saying is correct, that the first derivative test basically only tells you it's a local max, but then sort of additional thinking shows you that that in fact is the global max. So sometimes you need to think a little bit more. You need to apply your knowledge. Any questions about this problem? Let's see if we can do a more complicated one. Let's see. Okay. So somebody gives you a square, okay, and the side length is 20, and says, I'd like you to make a box out of it by cutting out squares out of the corners. Right, so you're going to cut these things out, and then you're going to fold the sides up. Fold the sides up, and you're going to make a box. Okay, so you've got a piece of cardboard that's 20 inches in side length, right? And they want you to make a box out of it, and they're saying, we want you to make a box with the maximal volume. Okay, so what x should we use to make a box with maximal volume? Julia.
It doesn't have a top.
Doesn't have a top. No top.
I don't take that into consideration.
You do have to take that into consideration. Yeah, there's no top. Okay. So let me ask some suggestive questions. What are we trying to maximize? This is a dumb question. Volume, right? What's the volume? How do we express the volume? Length times width times height, right? So what's the
20 minus 2x.
20 minus 2x times 20 minus 2x times the height of the box,
Okay.
x. Right? So the volume is x times 20 minus 2x squared. Okay. You take the derivative of that. How do you want to take the derivative? Somebody take the derivative of that? You want to, I mean, you can do it a couple ways. You could just multiply this thing out and then take the derivative, or you could use the chain rule. I mean, you could use the product rule on it. How do people want to do it? Product rule? Okay, so let's go the first guy times the derivative of the second guy, right? So you get 2, 20 minus 2x times minus 2, right? Then you get, so it's first times the derivative of the second, plus the second guy times the derivative of the first. And so you get negative 4x 20 minus 2x plus 20 minus 2x squared. Okay. At this point, what should we do? What trick should we play? Factor. Yeah, let's factor out a 20 minus 2x. Let's factor out one of the 20 minus 2x's. We're going to get here negative 4x, and we have here a leftover 20 minus 2x. Right. And so you get 20 minus 2x times negative 6x plus 20. Right. So you get, so what you get, x is either 10 or 20 over 6, in other words, 2/3. So again, right, we get 10/3, right? And if we want to think about this thing as a parabola, the thing is a plus parabola, right? It's an upwards parabola, so we get negative, positive, positive, right? Because the lead term is 12x squared. The lead term is 12x squared, so it's an upwards facing parabola, right? Right? So it's going to be like this. And that tells us that that 10/3 is it. Yeah, Nora.
So that means that it's positive beyond 0 too, right?
Yeah, but we actually don't want to consider anything. We actually have sort of a bound on this because our x should not be smaller than 0, right? We're not going to subtract a negative x out of here. And further, we're not going to go beyond 10 either, right? Because that would mean that we're cutting somehow beyond the constraints of the box. So really, we're looking between here and here. Yeah, thank you, Nora. I didn't point that out. Right. So, in fact, our x is constrained between 0 and 10 anyway. Right. And so what we see is that this guy is the max, right? Because we increase before it and we decrease after it. Okay. So that's kind of cool. We can figure it out, right? You need to take 10/3 as your height. Okay, let me set up just one more problem. I don't think we're going to get through it, but let me set it up. Somebody has a length of wire. Somebody has a wire, and the length of wire is L. And that person wants to make 2 fences out of that wire. So the first one is going to be a circle. So he cuts it into 2 parts, and then uses the first part to make a circle, and uses the second part to make a square. And the question is, how to achieve the minimum area. Okay. This is a mathematical farmer. Okay. And for some reason, the person wants to make this contain the smallest amount of area using the wire. I had my calculus teacher in high school was like a Christmas tree farmer from Boone, North Carolina. And I remember very clearly, he'd say, now, suppose you've got a wire. Suppose you got a wire. And I remember one kid saying, a what? Said, a wire. So I always think about my old calculus teacher when I see this problem. Anyway, let's start off with this problem next time.